So the next thing that I want to do is to do an example for chapter 12 on power amplifiers. And that example is going to be a problem from the back of the chapter. I'm trying to find out here which one. It's going to be problem 2 in the back of the chapter, because the issue with power amplifiers is when you're driving a lot of current, you start dropping voltage of your output. That is really, you have a gain of 1 for your voltage gain, and you start dropping some of that voltage on the transistor itself because the current is so large. So ideally, so this is problem 12 too. So ideally, in a power amplifier, you want the voltage to be at the same as your input for the sake of efficiency. And of course, at some point you're going to saturate on the power supplies, okay? Now, what happens is that you start getting this nonlinear characteristic that you can see it as the curve not being, the transfer curve not being straight, okay? So you probably have heard some of the, some faculty member talk about linearization and how they make linearizers. Well, they make these linearizers that basically look at this non-linear curve, and they try to make the amplifier or put something in the overall circuit to counter that non-linearity, so it goes back to this linear characteristic that gives you the maximum efficiency. And that saves a lot of, that makes the circuit much more efficient, saves energy, and allows you to, in the case of communication, transmit more information, because now you're not limited by this, you have more signal to noise ratio, okay? So that's what we're talking about. So what is this delta? Is very important for power amplifiers, and that's what this problem 2 deals with, calculating that. The second question is an adaptation, is a Cmos adaptation of a BJT circuit, which I'll draw. And some of the terminology or nomenclature that I've been using, it would be useful if you go back to chapter 5 on MOSFETs of the book and refresh yourself with some of these terms. For example, the overdrive voltage, which is the voltage that the gate gets driven above the threshold. So overdrive voltage is the VGS minus VT. So, you know, this type of simple relationships of the transistor, if you don't remember from electronics 1, you should go back and refresh yourself there. So, so again, this problem is based on a BJT, but let me read what the problem is asking. Let's see here. Look at my notes for the actual problem so I can read it. All right, so this is going to be a source follower. Okay, remember that a source follower is really a current amplifier, just like this power amplifier should be, as I've been mentioning, using an NMOS transistor, and is constructed following a pattern shown, they mentioned figure 12.3. So that figure 12.3 is an emitter follower base amplifier, which is you have positive supply here, and you have NPN there. Here you have an active load. So this is minus V, this is plus V here, and here's the output. With the load resistor. And this, the base here is biased with a diode and with a diode and a resistor here to ground. And the input is on the base of this transistor. So this is V in. So we want to construct an equivalent to this BJT topology using an NMOS. So what you would do, and I'm going to draw what you would do more on a chip type of design. So what you would do, you have an NMOS, just like we had an NPN here, and then another NMOS here, and that would be, so the output would be here with the load resistor. So this is VO, and this is VDD. Now in the book, and I'll finish reading the problem later, but in the book they tell us that VDD is 2.5 volts. That's important because you want to know how close you can get to that 2.5. So the degradation of the output is relative to the power supply. Ideally, you want to drive to the rails, but you can't. We're going to show what the non-ideality is and how close or how far we get from that. So this is going to be Q1. This is going to be Q2. And the input is going to come on the gate of Q1. And here we have, so this is going to be VGS1. And we're going to have active biasing of Q2, but a diode essentially is an NMOS with the gate and the drain tied together. So we're going to have here and that's going to be going to the source here, and that's going to be minus VDD. So that's going to be minus 2.5 volts. So the rails are plus or minus 2.5 volts for this amplifier. And this is going to bias Q2 here. And then we can have some type of resistor here to ground. And they tell us that that resistor is 1K ohms. Also, they tell us that the load resistor is 1K ohm as well. So let me go back and finish reading the problem, because it's based on this circuit. Okay, so keep in mind that circuit, because I'm going to have to erase it. But that, hopefully you can see how that's based off the BJT implementation. So let's see. So we have that. It says all 3 transistors are identical. So another thing is that all the transistors have a VT of 0.5 volts. And the mu, so mu, in this case, sorry, this would be, they're all N channels, so it would be the mobility of electrons, the capacitance of the oxide at the gate, and then the width to length ratio of the channel. That is 20 milliamps. So this is essentially the transconductance of the transistors. Not quite. Is the K? Is the K of the transistor? Milliamp per volt square. So that's the units for that. So we already know that VDD and minus VDD are 2.5 volts. They give us the values of the resistors. And what they ask us to do, as I started mentioning at the beginning, is this is the actual question. For linear operation, what are the upper and lower limits of the output voltage and the corresponding inputs here at Vn? So essentially, if this was a perfect, we would get something like that, ideally, and this is a flat here. And this would be minus 2.5, and this would be 2.5. But what we're going to see is that there's going to be a degradation when it starts, the nonlinearity starts, and they want us to find that out, essentially, what these limits are. So that's the question here. Okay. So the first thing that we want to find out is the current. What is the current that is going to flow out of the driver transistor, which is Q1, and that current is over here, and that current that is going to flow into Q2 as well. So that's going to be that current. So let's write the equation, and this is just a straight out of the drain current of an N-channel MOSFET operating in the triode region. So that current is going to be 1/2 mu n Cox VGS minus VT squared. Okay, and we know that VGS is 2.5 volts minus, so that's an old equation at the source of Q1, which is equals to 2.5 minus I. Okay. So, and I can essentially, since I have, I can work with milliamps for the current and work with kilo ohms for the resistances, and that is consistent with volts. So I can keep the units in that at that level, okay, and keep everything like that. So then, going back to the first equation, the current is going to be 1/2 mu n Cox times 2.5 minus I, because that's VGS, okay, minus VT squared. And essentially, I have, I know VT, I can solve for I, so that would give, and I have this quantity as well, so that gives me that I is equal to 1/2 20 times 2.5 minus I minus 0.5 squared, which gives me that which gives me that I is equal to 10 times 2 minus I square. And just to keep that going, I get a quadratic out of that, which is I square minus 4.1 I plus 4 equals 0. And if I solve using the quadratic equation, I get that I has two possible values, 1.6 milliamps, and but the only one that makes sense is going to be, the 1.6 milliamps. And that, if I use that current to solve for VGS, gives me that VGS is equal to 0.9 volts. Okay. So now I have to do a little bit of thinking. So I'm going to sort of write what that thought process is. So the upper, we're looking for an upper and a lower range, or an upper and lower bound. The upper limit of the output voltage, that is going to be when Q1 leaves saturation and enters triode, which is the equation we use, okay? And when that happens is when V, the input, is VDD plus VT. So the maximum input that I can have, because VDD is 2.5, is 3 volts at the input. Okay? And what we have to do for that input, which is the maximum input, so to obtain the equivalent or the corresponding maximum output voltage, we find the corresponding VGS1 for transistor 1, and then V out is VI minus VGS1. That's just an equation at that point for transistor 1 as a loop equation. And the other equation that helps me is the current through the load, which is the output voltage divided by the load resistance. And I have this expression for the load, and that's going to be the input minus VGS1 over RL, which gives me that VI minus VGS1. So IL, the current, the load current, is 3. So I'm trying to find what is the maximum voltage. So now I substitute for Vin max. So for the max, I substitute Vin max, which is 3 volts, minus VGS1. And then I can go back to my transistor 1 equation, which I'm going to write next. So the drain current for transistor 1 is, and that is another equation at the source of transistor 1, is IL plus I. Remember, we define I as the current going into transistor 2. And that is going to be 3 volts minus VGS1 plus 1.6, which is that current that we calculated, the current going into transistor 2, the 1.6 milliamps. So that gives us 4.6 minus VGS1. And if I substitute that into the transistor equation for transistor 1, which is 1/2 mu n Cox WL VGS1 minus VT square, I can find then what VGS1 is. So this is going to be 4.6. We found that out already, minus VGS1. So I'm just working with that this equation here. That's 1/2 20 VGS1 minus 0.5. That's the VT square. And again, I can get a quadratic out of that for VGS1. So I'm going to have VGS1 square minus 0.9 VGS1 minus 0.21 equals 0. And if I solve that quadratic, I'm going to get that VGS1 is 1.09 volts. So the corresponding maximum voltage is the corresponding maximum input voltage minus that VGS1. So that is the degradation that is being introduced by the load current at transistor Q1. So that is 3 volts that we had calculated minus the 1.09 that we just calculated. And that gives us that the maximum output voltage is 1.91. Oops. Let me just rewrite it here. So we had VO max, the output is Vin max that we had, minus the VGS1 that we calculated. So that was 3 minus 1.09, and that gives us 1.91 volts. So that gives us the upper limit of the output voltage. And the lower limit, so the lower limit of the output voltage is when Q1 cuts off, when it turns off. And at that point, I can have two situations. First, the output voltage is going to be minus I times RL because the transistor Q1 is cut off. And we already know the answer to that because we already calculated what that was. We already calculated I, and that was minus, in this case, going to be minus 1.6 volts. So that's one condition when the lower limit of the output voltage happens. The other one is when Q2 leaves saturation and enters triode. So just like we did with Q1, at that point, VO is going to be minus VDD because we do have that negative supply below Q2 plus the overdrive voltage for Q2. Okay. And as I had mentioned, the overdrive voltage is VGS minus VT for transistor 2. So now I know what that is. This is 0.9. We have calculated that, and VT is 0.5 volts, which gives us that the overdrive voltage is 0.4 volts. So if we go here, for this second condition, we have that VO is minus 2.5, okay, plus 0.4, and that gives us minus 2.1. But this happens first. So once I get that to that limit, it's not going to keep going down to minus 2.1. That's it. That's the best I can do on the negative side because it happens first. After that, since Q1 is cut off, I'm not going to be able to drive any lower, and that's going to define my range. Okay. So since this one happens first, this one becomes VO min. Okay. And the corresponding, if I can just I can erase all of this because that's not going to happen really. But we need to check whichever happens first. So now that I have the VO min, I can calculate the corresponding the corresponding input voltage for that VO min, and that's going to be VO min plus VT, which is minus 1.6 volts, or you have to really carry the unit, plus VT, which is going to be minus 1.1 volts. And that gives us both limits. So V out min and max corresponding V in min and max. So if we went back to our graph here, how is this amplifier going to really perform? We have that VI min, let's say, is somewhere over here. So that is minus 1.1. And VO min is going to be minus 1.6. So let's say somewhere over here. Minus 1.6. And for the maximum, we have VO max is 1.91. So somewhere over here. So 1.91, and VI max is 3 volts. So somewhere over here. Ideally, let me show these points here. And let's show, so let's say that over here we have minus 2.5, and here we have 2.5, and here we have, trying to, there, minus 2.5 there, and 2.5, well, that would be like way up here. That's not to scale, but the point is that the ideal curve would be something like this. The ideal curve would be something like that. And what we get out of this amplifier is something like this. Oops. It's something like this. Something like that. So that is the distortion and the nonlinearity of the real amplifier versus the ideal case. And that's why we need linearizers. So this gives you some, this is the kind of the main issue with power amplifiers. And that's why I wanted to show this this example. Any questions, anything that you want me to go back to? I know there was a lot, but that's the example that I wanted to present. Any questions at all?
I have a question. On the VI axis, so the VI max is 3. What is the number on the left side? It's 2.5?
Right. So basically, I tried to put just the, if you have a power supply of plus or minus 2.5, you would think that the input also is going to be bounded by that. In reality, you could drive it higher. That's what it says. The analysis says that you could drive the input higher than the power supply. Maybe you take advantage of that, maybe not. And in that case, your input, gets stuck at 2.5. But that's what it's showing. We found that the maximum allowable input was 3 volts, and this is the power supply. And for the ideal case, when you put 2.5 volts, you get 2.5 volts out. That's this point here. And for the real case, you can put up to 3 volts and you'll get 1.91 out.
Okay. Thank you.